Hello! Today I'd like to talk about Temper, a new programming language designed from the ground up to translate to all the other programming languages. Our motivation for this? There are some hard problems in distributed systems and they're getting harder. We need some integrative technology that ties them together. Temper is that. It can make your life easier, and this demo will show you how. By the way, if you work in an org that maintains a website, some mobile apps and server software, and maybe has some data scientists, congratulations! You're working on a multi-language distributed system. Temper is designed to fill gaps in distributed systems engineering by sharing rich type definitions and business logic across languages. What is Temper? It's a new programming language, a general purpose language meant for industry. It's designed from the ground up to translate well to all the other languages, so a team using it can produce libraries that support all the other language communities. Let's take a look. Here's Visual Studio Code with some Temper code. You can see that it looks like a markdown description. The English prose explains what the code does and why. The indented code sections are Temper code. It looks like any modern language that uses curly brackets and semicolons. This defines a price type. It's based on an ISO standard. Writing in Temper, we get a library for prices in all the other languages. Later I'll show you how sharing types across languages helps us in the demo. Here's a simple class definition. A price pairs a currency code, like USD for US dollars, and an amount. This class is pretty simple, but it has some logic. How to format a price is somewhat subtle because of minor units, which are explained in the prose at the top. Back up here, we have this @JSON decoration. That'll come in important later because for the demo, we're going to be sending prices between nodes running in different languages. But first, let me show you what it means to use this from multiple languages. This next part is pretty code heavy, so if you're more interested in high-level architecture and engineering coordination problems, you can skip to the next YouTube chapter mark. We've designed Temper with code exploration in mind and with deep integration into other languages' toolchains. A REPL is just an interactive playground. Temper REPL-BJS means start the JavaScript language's REPL with the JavaScript translations of Temper. The -W flag points it at the same directory VS Code was looking into. It's dropped me into Node so I can write some JavaScript. The table here shows that it's pre-imported the cart demo library translation. So I'm going to bring in that price type we looked at. Cart demo, by the way, it's just a regular JavaScript module. And price is just a regular JavaScript class. Remember, in JavaScript, classes are represented by their constructor function. So let me just go ahead and get the string form of that to show you that it's class. Yeah, price is just a class, and we can use it normally. So let's go ahead and create a value, new price, and a price is, its constructor takes a currency code and a value, so I'm just going to say $5 US, 500 cents, right, because of minor units. And let's take a look at what that price is. Remember, in the Temper code, I showed you that there's some custom formatting logic that shows up when we just do JavaScript that coerces the value to a string, as you might expect. We've put a lot of work into avoiding any awkward virtual machine embedding. Temper just translates its classes to JS classes and its functions to regular JavaScript functions. And a JavaScript developer's typical debugging and exploration workflow just work because of that. So tab completion, let's take a look at currency data, and we can figure out what's on currency data. Oh, we've got a minor unit, and for example, US dollars, 10 to the 2 is 100. There's 100 cents per dollar. So that's giving us kind of, you can go from a price via tab completion and, Temper's translated logic and realize that the current currency has 2 minor units. I pointed out the @JSON decoration on the temper code, and that allows for JSON interop. JavaScript's built-in JSON conversion functions kind of work with this, so at least the stringification. So if I stringify P, I get a JSON record where the currency code is what and amount are what you would expect. Let's briefly look at a statically typed language. So here's JShell. Temper-B Java dropped me into JShell, and it's given me some information about the libraries that are available. So I'm going to go ahead and import cart demo, and I'll show you the equivalent JSON conversion for prices. I can declare a variable. The temper price class just translated to a regular Java class. So I can do the same thing. This time I'll try Canadian dollars. And 750 Canadian cents. You can see here that Java's toString conversion happened automatically, calling the temper formatting logic. Java doesn't have a short equivalent of JavaScript's JSON stringify, but we have all the machinery we need to do that. So JSON text producer, thankfully tab completion works. JSON text producer just accumulates JSON text. And so I've got a place to put my JSON. Now I'm going to do some type-directed conversion. So I mentioned the price type. I ask for a JSON adapter, and I'm going to encode my $7.50 Canadian to out string thankfully tab completion works. That's kind of a lot of escaping. So let me make that look a little prettier. Yeah, and we get exactly what we would expect. And we can go the other way. So I'm going to parse the JSON I just produced and show you that I get back an equivalent value. I get something called the JSON object, which is a kind of tree representation, and I can use my JSON adapter and I get back something with the equivalent string representation. And just to make absolutely sure that it is in fact an instance of the price class, I can ask that question and I get back true. So we have a simple type definition based on an ISO standard that we wrote once, and we got idiomatic code usable in multiple languages and a way to send values between different languages' runtimes. Next, I want to demo a system using temper end-to-end to show how centralizing tricky logic lets you cut a lot of Gordian knots in distributed systems. But first, modern systems are distributed, really polyglot too. Here's a diagram from Stack Overflow a few years back based on their developer survey. Technologies cluster, and they cluster by language community. Technologies that are close together are often used together. Up here are a lot of data scientists. A lot of backend devs are kind of down here. This is where a lot of web technologies cluster. And over here, we've got a lot of mobile technologies. If your organization has data scientists, web developers, app developers, and backend devs, you're conservatively using 5 to 8 programming languages internally. That's great. People get to choose the right tool for their job, but it also makes it hard to identify common problems and share a common solution. With Temper, when Python devs and Java devs have a common problem, They can share the solution. You write the solution in Temper, the Python devs get a Python library, the Java devs get a Java library. Temper is the right tool for context-agnostic code, core definitions in business logic. If the code isn't about something intrinsic to data science or about a mobile app or about the web platform, write it in Temper and use it by translation. At its core, it's a compiled language that translates to many other languages. JavaScript and TypeScript, Java, C#, Lua, Python, and we're working on Rust and COBOL. Temper changes the economics of software development. A small team using Temper can support all the other language communities. I mentioned Gordian knots in distributed systems engineering. Briefly, the problems that I lived as Google grew from 100 engineers to 10,000 that led me down this path. Granularity. What can we share? We can share microservices. They're great, but microservices are stateful asynchronous functions. What if the thing to share is naturally synchronous or is easily explained in terms of types? What if I want to call it from within a tight loop and I don't want 30 millisecond transfer time? Transparency. The more we decompose monoliths into microservices or some other kind of distributed architecture, the less static analyzers like code checkers and bug finders can do. Each node is an island. Sharing type definitions on both sides of network pipes gives a basis for connecting those islands into an analyzable whole. Testability. As I'll argue later, end-to-end tests are necessary, but having a single source of truth for system semantics makes it much easier to maintain a rich test suite for the edge cases that are too small to warrant spinning up multiple nodes. Compositionality. Stateful functions are cool, but it's easier to solve some problems with a composable set of primitives. Libraries are better for that than functions. Migratability. We should expect well-designed systems to outlive some of the tools used to build them. Migrating systems is a lot easier when you have the ability to share business logic between an old system and a new while the replacement is being stood up. An awful lot of migrations fail because you keep needing to update the old system while the new system is coming up, and that's just this huge distraction. Onto the demo. Shopping carts are boring, but people understand them, so I'm going to use them as a running example. And they have surprisingly complex semantics. Here are just a few of the sources of complexity. You might switch currencies if you decide, oh, I can't get it online because it's not available. I'll do on-store pickup on the other side of the border. It's out of stock here, but not there. Shopping carts should be editable by the shopper, of course, but also customer service might be simplest for them to dive in and actually just make a change on the customer's behalf, especially if the customer has phone access but not device access. Going back to our Stack Overflow technology clusters, but here I've overlaid some of the nodes in our distributed systems on top of the language communities that are probably maintaining those pieces. We've got a server and a database. That language cluster here keeps track of shopping carts for users and eventually turns shopping carts into purchase orders. The server is authoritative when it comes to things like price and availability information. But for that to happen, Alice, our user, needs to create a shopping cart via web interface or mobile interface, or both. These two different language clusters over here. But if Alice runs into problems, she might call customer service. Often that involves code in an ERP suite. A lot of code that was not originally written by the organization, but with customizations. The customer management system might be this language cluster over here. Bob, a customer service representative, uses that to edit Alice's cart on her behalf. And finally up here, maybe we've got a data scientist doing some business intelligence. Maybe running Monte Carlo simulations, which are going to give more accurate results if they're running the same logic locally that the servers use to do it for real. And since Monte Carlo simulations have to run in tight loops, it's best for them not to be continuously pinging microservices. This diagram shows one sequence of interactions we might be interested in. Alice uses a client to send a message to a server. gets back the website, sends some changes. She then talks to Bob, the customer service agent, who uses the CMS to load Alice's details. He then adjusts a count. That gets sent back to the server. When Alice finally manages to reconnect, she sees those, she pings for those changes, gets them back, and lives happily ever after. Hopefully Bob does too. I like Bob. Back to VS Code. Again, feel free to jump to the next chapter if these code details don't speak to you. Here's another file in that same temper codebase. We define a cart as a list of entries. Each entry is something like 10 bananas. Each cart has a location as well, which it's just a postal code wrapper. The location type defines logic that lets us figure out things like the prevailing currency. In a real system, it might also distinguish between online shopping and in-store pickup or delivery. Going back to our cart details, each cart entry has information about whether a product is in stock and its price. Stock status is a sealed interface. Like Scala and Kotlin, that means that it's a discriminated union. Either its status is unknown, or we have pricing and availability information. Here, we're defining something we call the cart delta. Clients make changes to a cart, and the server needs to augment them with stock information. So clients are sending deltas, the server is incorporating them, and actually the server is sending back deltas saying, here's what changes I actually made, here's the details that I'm authoritative for, and perhaps here's some changes made by other clients that you're not yet aware of. You might have noticed that a lot of these values have marks associated with them. Marks are what let the server resolve conflicting edits, what gets us to eventual consistency. For example, if changes are made on a mobile device which is off network, it can save those edits and let the user keep making changes, accumulating edits that then get synced when they reconnect. Client marks allow for resolving those conflicts. Maybe two different clients change the same thing. And the server needs to be able to answer questions like, what are all the changes since the last time we connected? The server mark allows for that because it's immune to clock skew by design. And further down, here's a useful generic function that allows for picking the later of two conflicting changes. It's used over here in merge cart, which is an important abstraction. So we've defined types with important semantics. A server and multiple clients can collaboratively edit a shared object by passing deltas back and forth. And the cart also defines some logic for itself. There are a number of problems that might affect purchasing items in a cart. If you're editing offline, you might need to know some of those problems. You can't get a comprehensive list because you're not going to be getting stock and availability information, but you might get some other details. And one of the nice things about this, having this logic built in so that when you have up-to-date stock and availability information, you can compute the problems and have common presentation logic for displaying them to the user. One of the nice things about this is you don't need to send these in JSON. You can have very kind of trim JSON messages, not sending large amounts of kind of supplementary data back and forth. This kind of protocol design work, designing for eventual consistency among multiple views of the same thing, is the bread and butter of distributed systems engineering. It's super nice to have the entire semantics specified all in one place. Let's dive into the Java and JavaScript next that use this. I wrote a simple Jetty server in Java. It's about 350 lines of code because the important business logic is all shared even though Java is an older verbose language. Before we dive into Java code, let me just fire that up. Okay, I'm Maven installing my cart demo code. Oh, and you can see here that it's run some tests. Just a quick aside on that. Let me go back to VS Code. Here's the temper code again. This test block specifies code that isn't production code. Because temper code can embed in Markdown, you can have a narrative structure. For example, here's what we're doing in Y. Then the production code. Here's how it must do what it does. And interspersed with that, you say, for example, given this input, this function produces this output. Of course, a test being an automatable example of that. So yeah, we've got this block. We're setting up our marks. We're setting up a cart via mobile app, and then we're invoking merge cart, advancing time, getting more changes, and towards the bottom, we just have a series of assertions that everything kind of worked out. We've abstracted away the network connections. We've abstracted away how we encode things when we're going over the pipe. And we don't need to spin up a server in a database to kind of check this fairly involved example. Let's go back to our console. We translated tests. That test that I just showed you got turned into a JUnit test, which Maven automatically picked up and ran. So tests tend to be structurally simpler than production code and simple to translate. You get confidence in the Java translation from tests translated into Java and run just by the normal kind of CI/CD flow. Okay, I'm running the Jetty server now. And it's doing some stuff, grabbing files it needs, JavaScript files and that kind of stuff. So I've got a startup script. It's running. So I'm getting logging messages from that server. So let's switch to the browser. Here is our web client. You might be thinking this is kind of ugly. Is he really using a marquee tag? Well, I am a programming languages person with a focus on reliability and security. So I tend to leave visual design to the professionals. But bear with me. I'm going to add something to the cart. One witty penguin skipping rope. The price is unknown. I haven't told the server what my location is. In a real system, you might get a you might do IP auto detection. In this case, I gave it a zip code, and now I have a price in US dollars. And if I put in a Canadian postal code, it switches to Canadian dollars. All these prices are lies. Now I'm going to disable the network by clicking this checkbox. And, I am connecting to 127.0.0.1, which means there's really no other way for me to disconnect the network. So I just hacked in some JavaScript to, force any network sends to fail when that checkbox is checked. Here's another client. This one is connected. It pinged the server and it got the current state of the system. Let me go back to the one where it's disabled. Maybe I'll add something to the cart here. Now I'm accumulating local edits and I'll update the count. I'm not getting price information, obviously, because I'm disconnected from the server. And maybe I'll update this one as well. Now I don't know the price. I don't even know if they're available anymore because I'm asking for more of them. And here I'll go and I'll change this back to a location in US dollars, and I'm going to add something else to the cart. So you can see that I'm accumulating prices up here. It's waiting for information. I enable the network, and I'm going to eventually ping the server for more information, and I get my changes, plus I get the changes made on the other client. I've got up-to-date pricing information. Apparently, all of the things that I chose were available, and I've got no problems here. And over here, kind of the same thing. Although, the SKUs are showing up in a different order. So we've achieved eventual consistency. Both clients and the server have the same understanding of the shopping cart object. Let's see how the Java and JS code heavily relies on libraries translated from the temper to get all that to work. The Java is around 350 lines of code, counting import statements, comments, and blank lines. The JavaScript is 400 lines of code, a bit bigger. I didn't use any frameworks, so DOM edits take quite a bit of code. Server has some paths for serving static files like the JavaScript client. Here's where we generate the HTML for the client. Up here, we're getting a cart delta by subtracting the empty cart from the cart. And then we turn that into JSON. You saw me doing something similar in JShell. And we use that down here. We're going to pass that after, escaping it, along with the server's mark saying, what I'm giving you is accurate as of this server mark. And we're passing it to the JavaScript apply cart delta. So this is just, kind of priming JavaScript's cache. And if I go down a bit, right about here, here's where, the client sends me a message and I'm responding. So the client is saying, here's some edits to the shopping cart. Please apply those and make sure that I have the most up to date. And so, it's minting a new server mark. It's calling the temper merge cart function. I told you that was important earlier. It's kind of some core logic. And it's giving it the cart before, the delta, and the newly minted server mark. And so that newly minted server mark is going to be applied to anything that changes, and also to, of course, things like pricing information. And it's passing in a function which, in a real system would call out to a database for pricing and availability information. And, this all happens inside a critical section. So here is where its current view of the cart becomes the one after the changes were applied. And, this critical section in a real system would probably be a database transaction, right? Now, a ping is just a pair of a cart delta and a server mark. So the client sends a ping to say, here's the delta I want you to apply, and here's the server mark that I know about. The server then computes a delta to make sure that is sure to include all changes since that server mark, and it sends back that delta along with a server mark and saying, and now you're up to date as of this mark, right? And so, we use our JSON text producers and encoding to JSON to turn that ping back into a message that we can send to the client. And this, a quick aside about this JSON, this is type-directed conversion. Ping.json adapter. From a type, I can get an adapter that knows how to encode and decode values of that type. For a generic type, you also need to pass adapters for kind of relevant type parameters. This lets us keep messages small. There's no need to put verbose class names inside every JSON record. For example, we can encode dates to 8-digit strings, since when you're decoding a date, the decoder knows a priori that it is a date. It doesn't need to infer types from JSON structure. It doesn't need some kind of type identifier like Java util concurrent local date. Don't quote me on that. It doesn't need to infer types from JSON structure. So this lets us avoid semantic tar pits like reflection that are hard to translate, and means that any code analyzers are going to see what's going on instead of it being hidden in magic code. And to compute that message that we're sending back, we call another temper method, diffcart. We used that earlier, diffing with the empty cart to compute the cache priming. We're using it again to make sure that the client gets the differences between after and before, as well as all of the differences since the last S mark that they know about, and the new hotness S mark. Over to the JavaScript code. The JavaScript has its own view. It starts off as an empty cart, and the server, of course, kind of primes its cache. And it has a last no and S mark. We just choose 0 as, there's nothing to know. So that's got to kind of be a fixed point. And it can accumulate changes. I'll show you where that happens in a little bit. All of the changes, both from the server and those made locally go through this apply cart delta function, um, you know, which if it needs to, it decodes it, then it calls that kind of big semantically critical function translated from temper. It calls this merge cart. Oh, and cart demo here, it has the same meaning that I showed you in Node, where just, of course, importing our translation as a normal JavaScript module. And the edit buttons all go through this apply cart delta as well. They go through something that accumulates the changes and then applies the delta to the local view, right? Down here is where that happens. So we're using temper's plus method to add two deltas to get a delta. This is how we do accumulation. Make sure that we're scheduled to send that to the server to get pricing and availability information as fast as possible, and to update our local view, which then cascades into changes to the UI. And here's an example of something that is invoked by an edit button. It just creates a delta and then applies the user change. Farther down, we're going to see where we actually send messages. And like I said, a ping is a combination of a delta and an S mark. And no need for critical sections because Java is event loop concurrent, but we're using our ping JSON adapter again to encode to JSON. JSON.stringify would work in this case, but just, parallel code, sometimes easier to demo. And so that's how we come up with the body for our message. If I'm not doing shenanigans with checkboxes, we send the message. If the response comes back okay, then we process it. And processing involves using another temper function, kind of the opposite of plus, which adds deltas. We have a delta subtraction. So we can say, oh, we successfully processed these edits that we sent to the server. This is a client delta. We might have accumulated more changes since then. Let's subtract those ones, right? And again, our marks help us, make this kind of idempotent. And so, we don't want to just accumulate deltas. When the server actually acknowledges that it got them, we subtract them out, which keeps our running delta small. And then we're going to decode the updates we got from the server and apply those as well. So if any of our edits were conflicting with other ones and lost that conflict, this apply cart delta will bring our user interface up to date with the new changes. Down here at the bottom, this is where we just periodically ping the server. So we just schedule a send to the server. Typically that our accumulated deltas are going to be empty, so we're just sending back the empty cart and saying, please give me any updates since that, but occasionally it's not, right? I talked about testable systems earlier. If I wanted to test an interaction like this, and the business logic was spread across a server and a client and an ERP suite, the only way to test might be end-to-end tests. First, fire up a backend server in a test environment connected to a test database. Fire up an instance of the CRM server. Instrument a headless browser to fill forms. Interrogate one or more of those clients to figure out if the result looks right, and pray that all that asynchrony doesn't make the tests too flaky and that they don't just become a maintenance burden. Some end-to-end tests are necessary, but remember how the server and client code just delegated all the message management to temper code. Here's an example of a resolution scenario written entirely in temper code. All this requires is spawning a process that runs this test, and the entire complex interaction is captured in a little bit over a page of code. For critical systems, you will always need some end-to-end tests, but combining a modest end-to-end test suite with a large suite of unit tests that cover semantic corner cases will lead to a more robust maintainable system. Since Temper lets you get all of the message change semantics, all of the business logic in one place and use it where you need it, now your unit test suite can actually test all these corner cases. Going back to the big picture, to do this without Temper, you need a lot more code. You need to write and maintain code like the merge and diff-cart functions and the delta additions and subtractions in multiple languages. Here's the final tally. 1,000 lines of code in Temper, about 650 lines of prod code, 350 of test code. In a real system, you'd probably want that opposite ratio. I'm just writing this for a small demo, so I didn't test every conceivable corner case. I've got 350 lines of code in Java and 400 lines in JavaScript. Imagine there's a mobile app with the same size as the website. Another, 400 lines of code. These counts are low for real systems because it's bare bones, but they should still be comparables. With Temper, that's 2,150 lines of code. Without, a little bit over 4,000. Temper saved almost half initially because business logic really adds up. Perhaps just as significant, though, are the benefits to maintainers. Faced with translating all the Java business logic into JavaScript, more often than not, you get a poorly tested, buggy half reimplementation of some of the original. And when you need to change the semantics, that requires coordinating changes to multiple disparate, inconsistently tested code bases. That's an engineering management headache. With Temper, you change once, test once, and push library updates to many teams. Something that can be achieved by developers without engineering management stepping in. Having a single source of truth for your distributed system semantics lets you focus effort on producing one well-tested, high-quality implementation. So here's the spiel. Devs should pick the right tool for the job. The right tool for routing requests in a backend server and formulating responses is probably a language like Java. But if it isn't about web server stuff, consider Temper. The right tool for making HTML responsive is JavaScript. But if it isn't about that, Temper might be better. Similarly for mobile devices. The right tool for data science is a lang like Python. But Temper's cool too. All the code about shopping carts, how to define them, incorporate changes into them, calculate the total price, identify problems, all of that is better done in Temper. And an org that adopts Temper will benefit in a number of ways. Small groups of domain experts can figure out what should happen and how. They can focus specification and testing efforts. You get a lower code footprint and maintenance cost. A single source of truth for policy code means that domain experts have a single engineering point of contact to collaborate with to try out new ways of doing things. Small changes in business practices often need engineering management to coordinate software changes across teams when you've got multiple reimplementations of the same core idea. But with Temper, more can be done by devs working with domain experts. Rapid prototyping is easier when people can focus on specifying what the system needs to do without first committing to where that code will run. Migrating systems from legacy stacks can be easier when you can factor out some business logic or type definitions into Temper, then use it by translation in the legacy system with running updates, and also use it by another translation in the replacement system under development. Sharing some business logic helps a lot too. In the demo, we shared price localizations and problem messages. Obviously, that is a big help to mobile and web developers. It can also help if you have a separate system producing email marketing messages, like, hey, you created this cart, but you didn't, go through with it. And it's nice to have in server-side logging. Keeping feature parity between websites and mobile apps becomes a lot easier when you've got more ways to share code between them. If you're a VP or director of engineering, maybe you've experienced problems like this. Different teams break things for other teams. Management has to step in and sort out who is responsible for what. but it never seems to end. A certain amount of that is normal. But consider, if at the core you've got an object that needs to change in some ways and not others, a small team could focus on nailing those semantics down. Maybe some formal methods consultants could help. Solve that problem once, comprehensively, then have those other teams use libraries that encapsulate that logic. Consistent, well-tested libraries are what let us developers have nice things, and to build nice things. For developers, I think once you start looking around and thinking, what do I have to do in this language? And what could I share? You'll find that's quite a lot of code. We've been working on Temper for 5 years now. A lot of the early work was research into other languages and runtimes, but as I've shown, we've got the bones of a really useful tool. And frankly, though the language is a little rough around the edges, it's fun to work in. It's still early days and we're looking for early adopters. Hopefully, if you're as excited as I am about solving thorny problems in engineering robust distributed systems, or just about programming language design, or just about better ways to do your own work, you'll get excited about Temper. If so, drop me a line. I'd love to talk.